Hello, my name is Ron Aaron. I'm the creator of the 8th programming language. Today I'd like to talk to you in this tutorial about designing and implementing an application using 8th. Our goals today are, first of all, to familiarize you with 8th and how you can use it. Secondly, to get you involved in writing a simple and useful application, which you can use in your own daily work probably. Also, we want to discuss implementation trade-offs and why we chose to do certain things the way we did. And finally, we'd like to interest you in using 8th. The first thing that you need to do is to download 8th if you don't already have it. You can get it from our website. The free edition can do everything that we need to do in this tutorial. Second question that you're going to ask is, what is 8th? Well, it's a fourth derivative. If you're not familiar with the fourth language, it's a PostScript-based language. And it's has been used primarily in embedded work. Lately, there's a number of versions of Forth that work on desktop systems, and it's one of the less popular languages that you might encounter, so you might want to pay attention to what we're doing. The architecture of 8th is very similar to other Forths in that it has a simple interpreter loop which takes a look at any text that's entered and splits it up based on white space. When it parses off what's called a word, in other words, just a sequence of non-white space, it looks it up in the dictionary, sees if it's something that it knows. If it is, it does whatever it's supposed to do with that thing. If not, it tries to figure out if it's a number. If it doesn't manage to interpret it as a number, then it complains. And it persists in this loop until it's done. Now, unlike many other languages, like Perl for instance, it's not strictly interpreted. Your program is interpreted initially, and you can create compiled words which are actually compiled into native code. We'll talk a little bit more about that later. Advantages of 8th are compact size, true cross-platform applications, and as well encrypted applications, and if you have the professional version or greater, and in any case a high level of security based on a number of features. For example, that the libraries which are mostly used are all embedded in the binary itself, so the attack surface is much less than in the traditional systems. So, what are we going to try to do today? I want you to get your hands dirty with something very simple but very useful, an hour tracker. One of the things that I do for a living is write code for other people. And in order to get paid, I have to show them what I did and how many hours I worked. Now, there's plenty of solutions for this, but I spend all of my day inside of an editor, and I'd like to be able to take control of my hours based on some simple text that I can edit. So for me, the first priority is that it has to be convenient to use. If it's not convenient to use, I probably won't use it, or I'll use it improperly. The second thing, it needs to be flexible. And by flexible, I mean, among other things, that I should be able to easily account for small amounts of time, large amounts of time. I should be able to annotate however I want, and so forth. And finally, I want it to be easy to back up, because if I lose my accounting of hours, that's going to affect me negatively in the pocketbook, which is the whole point of this exercise. So let's start by just getting our hands wet with a very simple initial application. This is in your system, it's called the tutorial, TUT05. It's the fifth file in this zip file, which is available at a link below. So 8th programs start out simply as plain old text files. And you'll notice if you come from the Unix or Mac or Linux world, this shebang at the beginning, the pound bang sign at the beginning, is a common introduction on a script to let the system know that it should do something with this file based on whatever comes after that shebang. In this case, we're just simply telling it that it should be looking up the 8th executable and using it to interpret this file. Now if we go over here and we type in 205, which is this actual text file, we see it prints out hello world because I happen to have 8th on my path, and I've also made 205 executable. So because I'm running on a Mac, I can do this very easily. You can do the same thing on a Linux machine or a Raspberry Pi. If you're running on Windows, it's a little bit more complicated. You can't use this shebang thing, but I'm sure you can figure out an alternative. Now, the second line here starts with a backslash. Backslash is a comment character in 8th, and it comments to the end of the line. So everything after the backslash is a comment and ignored. The Vim incantation in there is meant to make my Vim editor happy and know that this is an 8th file and do a little bit of syntax highlighting to make things nice. So let's start with hello world. The very simple canonical start. Put hello world in double quotes like strings in most other languages these days. The period is the standard 4th-ish way of saying print this, whatever's on the top of the stack. CR is carriage return, bye means go away. So as you can see, it indeed, let me do this correctly, there we go, hello world. You could also simply do type 8th 205. This is how you do it on Windows if you don't have this sort of mechanism to launch the interpreter directly. Okay, so this is just to get your head around the general structure of a program. In fact, you could have done this just as simply by ignoring everything except for the hello world line and then just launching it with the 8th command directly. Now, let's go back to the basic structure of our program. Now we're going to sort of flesh things out in a way that will let us fill in the blanks as we go along. Sort of a top-down kind of programming style where we'll describe the words that we want to use. And let me just describe the word. In 8th and in other 4ths, a word is the basic unit of execution, what's called a function or procedure in other languages. So what we want our program to eventually look like is something like this. A word called header and a word called footer, and in between them some stuff, which is going to be the time information. So the rest of the program obviously looks exactly the same. Let's try to execute this one. Well, now we get a complaint from 8th telling us that the stack is empty on line 6. What's line 6? It's the word called header. Turns out that 8th already has a word called header. If we do this and we say help header, it tells us, creates a new dictionary entry named whatever, whose code is left unfilled and does not change to compile mode. Notice that the stack picture that's given in the help tells us we have to give it some kind of a name. So this header thing, there's no name after it, and so it doesn't know what to do, and it's complaining. That's okay, don't worry about it. If I didn't get a complaint at this point, I'd be surprised, because we haven't defined what header and footer and that vertical bar are supposed to do. Let's go to the next one. Now let's flesh out the 3 words that we just talked about, which again are header, footer, and the vertical bar. So here, first of all, we've got the vertical bar. what it does, what we want it to do, is we want it to let us write our hours, our time information, in a nice manner. What we mean exactly by a nice manner? Well, if you look down here, we have a date in standard year, month, day format. We have a range of times separated by a minus, and then we have some kind of comment, some kind of notes. Okay. To me, that's a very nice format because when you have it all listed, you can first of all sort by date, and it just looks reasonable. You may have another opinion on what's reasonable, but this is a simple format that we can deal with easily, and we'll show you exactly how we're going to deal with this. In our particular version here, the bar word, which we created by using the colon and the semicolon, colon tells eighth, or other fourths as well, start to compile a word definition. It's followed by the name of the word you're going to use, which in this case is just a vertical bar. Speaking of which, in eighth, any non-white space character is a valid identifier name. So I could type this in German, or I could type some sequence of random characters. Eighth doesn't care at all. It will use whatever I type in there. And the semicolon at the end means I'm done defining my word. Everything in between the name of the word and the end of the word is words that I'm going to use, or other syntax that we'll see in a little while. So inside of our bar word, we have parse line, which indeed parses the input stream. In this case, it's the file being read in. So the bar is going to parse the input stream to the end of the line. So it'll end up with this whole thing here on the first line, and this other thing on the second line. The dot we encountered before in the hello world, that means print, and CR we also encountered there means put out a carriage return. Footer prints a summary of the report. So MM we'll talk about in just a second. And we've got some incantation here. Now, remember I told you at the beginning that eighth is a stack-based language, or maybe I didn't tell you that, but if I didn't, it is. What that means is that the arguments to the words and the results from the words are placed on a stack, like a stack of dishes in a cafeteria. So in this case, we have mm, which is a variable defined up here. Okay, and then we do at. At means get at the value that's in the variable. So it takes whatever's in it, at, puts it on the stack. 60, well, that's just the number 60. /mod does divide with remainder. So it'll give me the quotient as well as the remainder from the division. This string here, total with some awfully sprintf looking text in there. This string is the format string that we're going to use to present the information, and unsurprisingly, s:\stir format means format the string that's on the top of the stack with whatever parameters are appropriate. Then we print it and we go away. So in other words, when footer happens, it'll print a line that says total, and then it'll quit. Header, which comes above, just prints a line of text that's column headings. And then the top of the thing is this var that we had. Now there's two ways to declare a variable in eighth. One is with var and one is with var comma. Var by itself will declare a variable that has an initial value of 0. Var comma will take whatever's on top of stack when it's being declared and stick that in the variable. In our case, we could have used var just as well. Now let's see what happens when we try to execute this. 07. So now you see It printed out our nice little header, and it's printing out every line that was parsed, which is exactly what we defined the bar word to do. And then at the end, it prints some total. Now you'll notice that the string formatting characters are pretty much, if you're familiar with C or Java or pretty much almost any other language these days, the way that you format characters, format the string is pretty much the same. There are a few differences which we will not get into because they're not important for our study here. Okay, let's take a look at the next fleshing out. Now, we wrote the parser there, the bar word. All it did was parse a line and then print it out. That's not very useful. So we're going to get the parser working now. So let's drop down to parse. Now you can see that this word has become quite a lot larger. Again, the word definition begins with a colon, it ends with a semicolon. Bar is the name of the word. There's some comments in the definition so that we can figure out what it is when we come back next week. So let's see again, what did we do? Parse line, again, same thing we did before, but instead of printing it out, we're doing dupe, which duplicates it on the stack. So now there's two copies of that string are now on the stack. And when I say two copies, that's not exact. The dupe word creates a new reference to the original item. Items on the stack are references to items somewhere else. So when we start up 8th, we put a string on the stack. If we do .s, which means print the stack, we see here the address of the string that we put on there, and we see a number there before the actual. Let me do this. This is the address. This tells me it's a string. This tells me the reference count. When I do a dupe, now I see it's exactly the same address, which means it's the same exact item, and the reference count is now 2. So here's another bit of information for you, which is that 8th uses reference counting to keep track of items. You do not ever have to, and you can't, allocate memory or free memory, all those sorts of things. 8th takes care of that in the background. Whenever the reference count of an item goes down to 0, it gets cleaned up. So in any case, back to our thing, we parse to the end of the line, we duplicate it, and then there's this funky greater than R. So I just said that it's a stack-based language. You have 2 stacks that you get for free. One is what's called the data stack, which is where when you do a parse line, the parsed string ends up on the top of that stack. The R stack is a secondary helper stack. Now, if you're used to regular fourth, you'll say, well, wait a minute, that R stack is the return stack, and it has to do with return addresses. That's true in regular fourth. It's not true in 8th. In 8th, the R stack is simply an auxiliary stack that you can use for anything you want. It has nothing to do with return addresses, and if you attempt to change the return address, to jump back to some other part of the code by modifying the R stack, it will not work in 8th, and that's a security feature. All right, so we have a string on the stack and also in the R stack. And why we're sticking in the R stack is a good question. We'll get to that in a minute. Here we're going to use a regular expression to parse the line that we just parsed. Okay, so the parse line really only parses off a line. It doesn't actually do any parsing per se. Here we take a regular expression, and if you're familiar with, I guess, Perl and a number of other languages that use the / as a regular expression delimiter, you should not be too upset by this syntax. So here we have a regular expression which has four sub-expressions, 4 capturing parentheses, and what it will do is it will the first one will get the number, the year, the date information. The second one will get the time, the start time. The third one will get the end time, and the last one will get a comment if there is one. R match means regular expression match. So we gave it a regular expression. It's got a string. We give it a regular expression, and we're saying match it. R match will tell you how many things it matched. So if it didn't match anything, it'll return with a 0. So not if, meaning I wasn't able to do anything, I wasn't able to parse it, then we'll print a could not parse the string that we stuck in the R register, the R stack. It'll come out and be printed also. So we could not parse, it'll tell you what you couldn't parse. Then it'll drop the regular expression, return, and now we have a double semicolon. Double semicolon means exit the function, exit this word now. So in other words, what will happen is if there's a failure to parse, it'll print out that it couldn't parse, and it'll tell you what it couldn't parse, and then it'll return to the next thing that needs to be done. But if it succeeded, it'll get down to here. And regular expression submatches start at 1, so it's expression 1, 2, 3, what you're familiar with PCRE is \1, \2, and so forth. So here we take the regular expression, and this is R colon at, not R at. R at would take it off, take something from the R stack. R colon at takes an item from a regular expression. And 1 to 4 loop. Loop will call this word, and let me tell you what we just did there. The parenthesis there means I want to declare an anonymous word. The colon gives us a word with a name. But we often want to just have a little chunk of code that does something, and we don't care to try to think up some great name for it. So in this case, we've got an anonymous word, which, being anonymous, has no name, and we feed it to the loop word. Loop needs to have something to execute, and so this is how we do it in eighth. We don't have standalone for loops, we don't have standalone begin, end, those kind of things like standard fourth does. So 1 to 4, it'll use an index of 1, 2, 3, and 4. It'll loop over, it'll execute this word 4 times, and on the stack, it will push the index of that particular time. So it'll say 1, and then it'll go into there. It'll go 2, and it'll go into there. So what we do in here is R at, when it comes into this code, the stack will be index. I'm sorry, it'll be regex and then index. So the R at word takes exactly that stack picture, takes a regular expression and takes an index to look into. R at will give us the sub-expression for that number, and then we swap it. So using sort of array terminology here, after R at we'll have Rx, and then Rx whatever is at that index, and after swap it'll be like this. So that's after each iteration, and what we'll end up with is at the end Rx1, Rx2, and so forth until 4. And because the regular expression will be at the top of the stack, we're going to drop it when we're done with the loop, because we don't need it anymore. And so at the point where we've got this, we've basically unfolded the regular expression. We've taken the regular expression matching, and we've picked out all of the pieces that we're interested in. And then we call process line. And when we're done with process line, which we'll explain in a minute, we drop whatever was on the R stack. Okay, so process line. In our case, like I said, it's going to get 4 items on the stack. It's going to get the date, the start time, the stop time, and some kind of a comment. Now here I put a comment to do because we haven't really implemented it. We just have some code here that's going to print out some information. So if we run this time, we're going to see that indeed the output is different from what we had with number 7. Number 7, we printed out the entire line that was in the code, that was in the document. And this time, we're printing out parsed information. So this is what the regular expression picked up as the time, the beginning and end times. Okay. The rest of the program is actually the same as the previous one. All right, let's go to the next one, number 9. In this one, we're going to process the line data. So now we verified so far that we can parse the information correctly, and we can split it out in what looks like the correct fashion. So now, we're not going to satisfy ourselves with just printing out the information. We're going to look at this process line in a little bit more detail now. So what are we doing here? We're going to actually process the information. So, as we get into this, we're going to realize that sometimes we're going to get a comment that's blank, and sometimes we're going to get a comment that doesn't exist. In other words, if there was nothing there at the end of the line after the end time, then the regular expression will give us a null for the fourth sub-expression because there was nothing there, which is not a problem, but we need to deal with it. I mean, it's a valid possibility. So, as I said, comment's going to be on the top of the stack. We check to see if it's null. Is it null? And in eighth, null is a specific and unique data item which essentially usually flags a problem or missing data. So in our case, it means either the data wasn't there. So if we come back with null, then we drop that because we don't want null, and we replace it with a blank string. And then we stick the comment onto the R stack. Now, what we have after we've removed the comment, we have the date, the start time, and the stop time. Well, the start and the stop time are hour, colon, minute, minute, and they're strings. So how do we deal with them? Well, we write a little utility word, to HHMM. Okay, and so we do that, swap to HHMM, and subtract n numeric minus. So what's 2HHMM do? It's right here. It says, well, let's split the string. S divide means split the string on colon, because it's going to be HH colon MM. And that string split will give us an array. And by the way, we don't have to do any error checking here because the regular expression will match an character, colon, character, or rather, number, colon, number. So since that's the case, we already know that when we get to this point, the string that we're being given here is a valid string. So we split it on the colon in the middle. S slash will give us an array with the components, and then we open the array. So now on the stack we're going to have hour, minute. But they're strings. Strings don't help us. So we're going to convert them to a number, to number, swap to number, and then we do a little bit of multiplication. 60 times the number of minutes will leave us minutes, and I'm sorry, we have the hours on the top, now. We multiply by 60, that gives us the number of minutes. And then we add in the number of minutes. So this will convert a string of the form hour, hour, minute, minute to the number of minutes. That's all. That's the whole purpose here. So now at this point, after that's done, after process line's gone through that, we have our time information on the top of the stack. What that means is we have the date, which we haven't touched, the minutes, which is the number of minutes in the interval that was put on that we indicated, and on the return stack we have the comment. Okay, and then we do this new word called new day, and in our implementation here it really doesn't do anything but print out the information. So let's see what it does on 209. Okay, so you can see here we have the date, the number of minutes, and then the comment. And it's still telling us that the total is 0 hours, which seems wrong. It should say 1 hour, right? Well, we didn't do any coalescing of the data yet. Let's go to the next one. Here we're going to flesh out the word new day. So new day is kind of a long word here. Okay, you can see it goes all the way down here. Generally speaking, in eighth and in other fourths, you want to keep your words short. This word could have been shorter if we eliminated all the comments that are in it. That's number one. And also, typically, you would have put more on one line. However, it's still kind of a long word, and we probably should split it up. But for our purpose here, we're not going to do that. So, new day, like we said, takes a date, takes a number of minutes, which were worked on that date for this particular line entry, and we have a comment in the return stack. So we start off with this word called over. Over takes the item underneath the top of the stack and puts it on the top of the stack, while not removing it from its original position. So before we had date minutes on the stack, we started with date minutes. After over, we'll have date minutes date. Okay. So the purpose of this next chunk of code, this here, the purpose of this piece of code is to check and see if we're starting a new day. Because what we want to be able to do in this is to have a number of entries for any particular day, because as you can see from the format, we're only allowing one time range per line. So what we want to do is we want to allow multiple entries for a particular day. So when the day changes, we want to print out the information for that day, because in addition we need to accumulate the information for a specific day as we go along. So here we take the year, month, day, which is a variable that we've declared above. In fact, there it is. Here, let's just talk about the three variables that we added here. We added one called today, which is the number of minutes accumulated today. Comment is an array that has whatever comments were accumulated so far. And YMD is the last date. So, going back here, we take the value that's in the variable YMD at, and we compare it with this date that we were given, S equals. If the string is equal, not. So if the string is not equal, then we do this. The string is not equal when we have a different day. So we take today's accumulation value, we accumulate that value into the total number of minutes, then we print the day, we reset then the comments and the today. Now this print day is also a little bit busy, but here we print and then we reset. And then After we've done that, regardless of whether it's a new day or an old day, we accumulate today's information for it. We make sure that we're keeping track of that date in our day string. And then we only want to accumulate comments which are neither empty nor null. So we get back the comment value, the comment that was passed in. We trim the string, which means remove white space from both ends. We check the length. If it's got a length, then we push the comment into the comment array. Okay. The other thing that we do here that's interesting is the print day. So print day does this. It says today, number of minutes. We're only going to print lines for which, we're only going to print days for which the accumulated number of minutes is not 0. So you could have an entry with the same start and end time, in which case you'd have a 0 number of minutes, and so we're not going to print that. Also, when we start, the value of today's minutes is 0, and we don't want to print an empty line at the beginning. So today, we get the value of today's minutes, duplicate that, and see. If a value evaluates to a non-zero number, then it's considered to be true. So if a number of minutes is not 0, then let's print the date. Let's convert the time back into hour, minute format. Remember that the time is a number of minutes. And coalesce the comments. So here we take the comments, get the value of the comments, and we want to join them with a comma and a space. And that's what this whole thing does, and it prints it out. So now let's take a look at number 10. Well, that looks promising. So we see that on 6-1, we had a total of 51 minutes. One line is project X, another line had a comment, add comments on it, which we can see actually here. And we're seeing something interesting too, that we got a project Y. That's because we simply added another line here. The previous one, we didn't have that line there. We added that in order to have something to show in the next screen. So again, we're seeing 17 minutes for project Y, 51 minutes for project X. Also, just to take a look at the HHM, from HHMM, we take the minutes, divide by 60 with keeping the remainder, and then we format it. That's all. So we're turning it into a string. It's the inverse of the function of the word right above it. Okay. Now we're going to refine the product that we've done so far. We're going to do something called, we're going to handle quantizing the hours and handle minimum minutes. Why do we want to do this? So different people have different approaches when they're billing. My approach on billing is that I'll bill in 15-minute increments, but I'll round up or round down. So in other words, if somebody, if I have an hour and 2 minutes, I'll charge a person for an hour. If it's an hour and 10 minutes, I'll charge them for an hour and 15. So the quantizing puts it on an even number, a specific boundary of minutes. So here we define the quantum as 15. You could change it to whatever you want, but 15 is what I use. And then there's a minimum as well. So if the number of minutes on a day, for example, I get out of bed and I have to do work for somebody and it's only for 5 minutes, if I were only doing quantization, I would round that back down to 0. But I had to get out of bed and do something for this person anyway. So I have a certain number of minimum of minutes that I will charge. So here I'm saying it's 25. That's not actually what I do, but it doesn't really matter. So let's take a look first at minimum and how it's implemented. So the minimum variable is used inside a word called minimum. Minimum takes a number, and it returns a possibly modified number and a flag, a true or false flag. As it says here, ensure that if there's any amount for a given day, it's at least the minimum. Returns true if the original value is the same as the returned value. So here we do dupe dupe. And why do we do dupe dupe? So now we've got three n's on the stack here. We have n, n, n. If. So if we'll only get in here if it was if the top n was non-zero. But since if consumes the top of the stack, we'll have nn. We take the value of the minimum and do n max. So n max will take the maximum value of either the minimum or whatever's on the stack. So that ensures that whatever number we have there is going to be at least the minimum. So when we get down here, we have n and m. So now we tuck, so we'll have m, n, m. And n equal will consume the top two items on the stack and turn them into true if they're the same, or false if they're different. So now we end up with the possibly modified number, as well as a flag which indicates whether or not the number was actually changed. So, how are we using it? Here, we get our today value, because we were doing this on a day-by-day basis. The new day, so we've got a new day that's different. We're going to check now and see if we change the minimum. If we didn't change the minimum, then we're going to apply quantization. Why do we do it this way? We do it this way because we don't want to quantize, well, we want to quantize a value in the middle as well. We always want to quantize the value, but we don't want to quantize it if we've already applied the minimum. Or we don't want to apply the minimum if we've already quantized it. So we want to do one or the other. And this is one way of accomplishing that. We could do it a number of other ways, but this is one simple way of doing it. Right. So we get the quantum value, which is in our case 15 minutes, and then we invoke quantize. So quantize takes an original number, takes the quantum that we want to apply, and returns us a quantized number. So this is a little bit interesting. What we do is we dupe save on the R stack. Okay, fine. So we're saving our quantized value. We could do tuck and get the same effect. We're going to do the /mod, get back our quantized value. Now what did we do here? The /mod basically is doing n divided by q with remainder. R@ is the original q, the quotient, the quantum. We multiply that out by the quotient. So now we have a number which is going to be not more than n, and then we swap out. So now we're going to have the maybe modified number and the remainder. Now we take the quantum again, divide it in half, and we say, is the remainder less than that? Then it's going to be 0. Otherwise, it's going to be the quantum. And then we simply add that back into our original value. So in this case, what we're going to do is we're going to say if if we're halfway If we're halfway to the next value, we'll go to the next value. If we're less than halfway, we'll stick where we were. And we'll drop the value out of our stack. So when we run this one, we get a slightly different version. Here you see that in project Y, we had 17. Hold on, where are we showing 17? Right, because we had, as you can see here, we added a little bit here just to make it a little bit more interesting. So the values are a little bit different. We have this be minimal value, which if we were just to use it directly, we would have a mere 1 minute. But as you can see here, it's 25 minutes, which is our minimum. And you can see that the other values are quantized to 15-minute intervals. Now, there's a lot more that we could do, but I'm running out of time right now, unfortunately. So I'm going to stop. And I hope that you have more questions, and you can feel free to ask on our forum. You can send me an email at ron@arentech.com. If you want to send me a message and ask questions, you can do it either that way or through the forum. And we'd love to hear your feedback. Enjoy 8th.